Thanks a lot for joining us today for Marek's talk on fusion of simultaneous equation models and Bayesian networks. Marek is a professor emeritus at the School of Computing and Information at the University of Pittsburgh. He holds a faculty appointment in the Computer Science Department in Białystok University of Technology in Poland, and I think it's from Białystok where he joins us today. Marek received his PhD in engineering and public policy in 1992 from Carnegie Mellon University in Pittsburgh in the US, and he is a recipient of the Faculty Early Career Development Grant from the National Science Foundation from 1996 to 2000. Outstanding, he had several awards, including Outstanding Mentor, University of Pittsburgh Chancellor Distinguished Teaching Award, and 2 Fulbright fellowships. His research interests focus on probabilistic and decision theoretic methods in decision support system and human aspects of decision support. He's widely known for the graphical modeling software Genie and Smile, which he has developed at the University of Pittsburgh, and it's commercialized and available at the link that is already in the chat. Before we get started, Marek, what is it in particular that you like about Bayesian networks?
What is it? Well, I actually have a sentence on one of the slides later that
oh, okay.
We can talk the same language with statisticians, philosophers, and engineers. So it's not some hocus pocus artificial intelligence formalism, but it's really science with a capital S, mathematics. That's what I like about them most, I think.
That sounds great. And before we get started with your slide, is there anything personal that you'd like to share with us, like hobbies or, favorite things?
Well, I do a lot of things. Recently I've been going on wild fishing trips. I haven't fished in New Zealand or Australia yet, though.
Ah, you got to come. I'm told there's great trout fishing here in whitebait and all sorts. Excellent.
Just in January, I was in Tierra del Fuego, Patagonia.
Oh, wow. Sounds amazing. Well, thanks so much for being with us today. Would you like to start sharing your slides and get us going?
Yes, I will. Thank you. Thank you very much for this generous introduction. I have, let's see, entire screen. Here we are. Very good. I assume you can see my screen. Thank you very much for the generous introduction. I prepared a talk for half an hour, more or less. So naturally, it's not going to be going in very deeply. I'll try to into the material. I'm trying to focus on the intuition, and this is what I hope to convey today. So, fusion of simultaneous equation models and Bayesian networks. Here's the overview. I cover a little bit Bayesian networks, structural equation models, then the dynamic counterpart, which is differential difference equations, and then tell you what we've been doing with that in theory and also with the software. So Bayesian networks, as you all know, they come from a brilliant idea by 2 people, statistician Philip David and Yuda Pearl, both brilliant researchers, and the idea is so simple: represent explicitly independencies in probabilistic models. Most brilliant ideas are obvious once you have them, but if you don't have them, you don't have them. They are not obvious at all. How is it used? When you have a factorization of a probability distribution, a Bayesian network essentially is a graphical representation of that factorization. You put arcs from the variables behind the conditioning bar into the variable before the conditioning bar. So here is a factorization and a corresponding Bayesian network. Different factorizations give you different Bayesian networks. The nice thing about factorizing and drawing those graphs is that if you have knowledge of independencies, you can simplify them and then obtain a simpler Bayesian network. Factorizations help you with drawing the networks, but independencies lead to absence of arcs. And that is the big, brilliant thing about them. To give you an idea of what it means, is here is a real model. You can get it from the repository of models of Bayes fusion. There is over 2,000 variables in this model, and there are many, many arcs, 3,600 arcs. If you look at it, it's a spaghetti. But it's more important how many arcs are missing. Over 2 million arcs are missing here from a complete graph. Those missing arcs allow us to reduce the number of parameters that you need to represent this model from 2 to the power of 2100, which is roughly 10 to the power of 600. If you wanted to represent it explicitly, brute force, you would need more numbers than a gazillion more than the number of atoms in the universe. So you see the savings and the brilliance of the idea of representing explicitly independencies and the idea of Bayesian networks. So now Bayesian networks are in new formats, just a few decades, not more. Structural equation models is a much older formalism that has been used in science, in engineering. Here is an example of a system of simultaneous equations. This is just an example, 10 variables, 10 unknowns. They are simultaneous, so you can solve them, you can solve for each of the variables. The first 3 variables are describing interactions among variables, the first 3 equations. The other 7 are equations for exogenous variables. There's no noise in this system, but you can easily add noise, which will make the whole the solution also probabilistic. You will have probability distributions, and just like in Bayesian networks. In early 1950s, Herb Simon, with whom I had the honor to work during my doctoral dissertation work, with him and also Max Hennion. Max is one of the also key people in Bayesian network community. As Herb Simon in 1950s has shown that for any system of simultaneous equations, you can draw a graph. He proposed an algorithm called causal ordering, and has shown that there is an asymmetry that you can make explicit in such a system. The intuition behind it is that a node and its parents corresponds to an equation. For example, you have an equation for student-teacher ratio involving number of students and number of faculty. Here is the equation, and you will observe it after deriving the causal ordering as a family in the graph. Now, the structural equation models, why structural? Many people use the term structural for linear equations, but structural equations can be of any form. Structural means that they are describing a unique mechanism working in the system. How do you know it's a mechanism? Well, there is a theory. For example, Newton's second law, force, mass, and acceleration form an equation, and it's also a mechanism that we know in theory. It's a theoretical mechanism that we know very well. So each of these describes some mechanism acting in this system, which in this case describes money flow in a university environment. The nice thing about systems of equations is that they support so-called changes in structure. That's an old term, early 20th century. In econometrics, they realized that that if your system consists of structural equations, then that system will predict the effects of manipulation, interventions. What is an intervention? For example, in the university environment, we can say, as a matter of policy, we want the student-teacher ratio to be 10. We impose it on the outside. To make it this system solvable, now we have 11 equations and 10 variables. We need to strike one of the equations out. Suppose, and there are ways of determining which you have to, the subset from which you need to strike it. Suppose we strike the number of faculty out, and the new system has a new causal ordering, new structure, which, if you rearrange it a little bit, looks like a 3-layer structure now. We still see the equations. The node and its variables are equations, but please note that this equation has reversed completely. Now we have the number of faculty determined by the number of students and student-teacher ratio. That's a trick that they knew in econometrics, but they didn't understand why that works. Simon has postulated that it's because there is causal information in that system. So there are the structure of that model, the structure of equations. In early 90s, Simon and I have shown that you can also, these are just to flash the important thing, that there's a theorem in the paper saying essentially that a discrete Bayesian network can also be viewed as a system of equations. Here's an example. If you have a simple Bayesian network like that, you can construct equations that essentially describe it. So it's a constructive proof. There are many possible systems of equations that you can draw for an existing Bayesian network. Here is one. It's a system of simultaneous equations. It turns out that there's also, if you have systems of differential or difference equations, the differences between continuous and discrete time. Differential equations have continuous time. Difference equations have discrete time. In Bayesian networks, we usually use discrete time, so we have difference equations. Just flashing you these, but I'll show you how that works in Bayesian networks. We have a famous model of predator-prey, Lotka-Volterra equations, two differential equations. When you solve them, the solution is a function of time. You can see the population of predators and prey as a function of time. You can also draw beautiful phase diagrams. These are the solutions of systems of differential equations. Another model, a Lorentz system, the famous butterflies, which are the phase diagrams for this system. The butterfly effect comes from this, the name comes from this system. What are hybrid Bayesian networks? Hybrid Bayesian networks are essentially networks in which you have both discrete and continuous nodes. You essentially marry those two formalisms. So here are the equations, Bayesian networks, and we bring them together. What are the advantages of that? You can build them so that they reflect the causal structure of the model, gives you the insight into the problem. You can easily accommodate uncertainty in both equations and Bayesian networks, as you know. You can reconfigure them. That is not an easy problem. The way I showed you, the changes in structure. In Bayesian networks, we have arc cutting semantics. We essentially cut the incoming arcs when we manipulate something. But there exist in real-world systems that actually can reconfigure, like the one that I showed you. The structure changes, the direction of arcs. The foundations are sound, and the last point is what I said in the beginning. That's why I like them. It's you can talk the same language with statisticians, philosophers, and scientists using Bayesian networks. Here is an example of a hybrid system. It's also in our repository. I can show it in a moment. We have continuous variables which are specified by means of equations. So a family, this node and its parents, is just an equation. And we can have discrete nodes as part of the models. And these are Bayesian networks. Before I go into the software to play a little bit to show you that live, the extended family of Bayesian networks is quite large. If you look at spreadsheet models, every cell that has an equation using other cells, that's essentially equivalent of an equation. And all the other cells that don't have equations, they are exogenous variables. So it's a member of that family. Of course, the user interface here is just terrible. It's so easy to make mistakes. In fact, the next member of that family, Visual Spreadsheets, it tries successfully to fix it. You can imagine every node in this graph. They're called different names. I guess influence diagrams is one way of calling them also. It fixes the interface, essentially. It's so much easier to operate with this kind of models. This is my favorite, Analytica, developed by my former advisor, Max Hennion. It's really a great system that has been an inspiration for many Bayesian network packages, including the one that we have been developing, Genie. Dynamic Bayesian networks is an extension of that. As I said, it's equivalent of systems of difference equations, where you define the number of steps and you can predict the probability or value of variables over time. You can plot it as, remember the predator-prey models. This is essentially showing you the probabilities over time. And then you can extend it also to influence diagrams. Some of you are most certainly working with influence diagrams. So this is the model of the world, a Bayesian network. Decision nodes can be viewed also as variables in a Bayesian network. The only thing is that they are under our control. So these are variables that we can perfectly control. We can set their value. And these, which are utility nodes, are, this is just a function, a value function over some of the nodes. So it's just an extension. The software, some of you know it quite well. We've been developing it for over 30 years now. We started in 1995 at the university. We were developing it for 20 years in university environment. It became quite well known, quite widely used. We did well in UAI speed competitions. It's been good, fast, friendly, and reliable. In 2015, we created a company to be able to develop it further. We have kept this original promise to make it available for free to academic use. So it is still available, and it will be, as long as I'm there. It's going to be free for academic users. Many modules, library, then there are wrappers, and then Genie, which is what you will see in a moment. I'll give a brief presentation of these ideas in Genie. So that the rest is going to be just software. So let me show you that. So what I'm doing now is I'm downloading models from our online repository. Let me show you that huge model with machine diagnosis. Loading takes time. So this is the 2100 variables model, the spaghetti of connections. As I will show you, it updates very quickly, really. It's a fraction of a second to update this model. Here are targets, they are going to be updated. So here we are, bang, it's done. It's so representation of complex domains, even though it's NP-hard, with Bayesian networks, it has become practical. We can do it, and this is a great thing about it. Let me show you this example of the hybrid model that I just showed you. Here we are. Some of the nodes are discrete, and you know them. If I double-click on that and look at the definition, it's a discrete node with discrete definition. When you have a discrete parent and continuous child, it's a special type of equation. Essentially, depending on the value of the parent, you have a different definition, different equation. And for that, you can use a conditional function like choose or if or switch. There are functions like that here in the set. So here we have essentially 4 different equations. They are very simple, just distributions, depending on the value of the season. And by the way, when we were developing this hybrid capacity, we wanted to give the modeler complete modeling freedom. So I know that there are Bayesian networks that implement linear equations, multivariate Gaussian distributions. And there are also other approaches that with truncated exponentials that also put limitations on what you can represent. Here we essentially say anything you want. So it's the problem that drives the representation, the definition, and all of these functions are implemented. If there is any function needed, we can easily add it to this. Distributions and functions. In case of continuous parent and discrete child, what we do is we specify for the parent, for the continuous parent, a discretization. This is how you want it discretized. And then the definition of a discrete child of a continuous parent is a conditional probability table conditional on those discrete values of the continuous parent. Then continuous, their definitions are just equations that are describing the interaction between the node and its parents. So here are 3 parents, and they will occur in the equation. The equations are, by the way, just engineering equation for exchanging heat in cooling or heating of buildings. So now, when you allow complete modeling freedom, the only algorithm that will always work is stochastic sampling. So we just do stochastic simulation, and what you see here is, in the result, you see a probability distribution derived by sampling. If you have sufficiently many samples, you can approach the precision with arbitrary. You can approach the result with the arbitrary precision. Stochastic sampling does not work when you have observation that has parents, because suppose I observe a value here. Let me enter evidence of 10 degrees Celsius water outlet temperature. If you have a point value here, stochastic forward sampling will not work because the probability of hitting that value in forward sampling is close to 0. If we do that, if that happens, what we do is we do discretization on demand. Nothing has changed in the model. It's still a system of equations, but we turned it into a discrete Bayesian network just for the purpose of inference. So in the discretization tab, you see the conditional probability table derived from the equations just for the purpose of inference. Genie and Smile are so fast that we can the inference. And now it's a discrete Bayesian network. You can make observations, you can perform inference with it, and work further. I'm going to wrap up by showing you the dynamic models, which is a recent addition. We added that just last year. So we are now able to model systems of difference equations. Let me show you the foxes and rabbits, the predator-prey models. All these models are from our repository, so you can load them. So here is a system of 2 difference equations, Lotka-Volterra equations. Here are the parameters of the equations, and what you see here is the result, which is the number of rabbits as a function of time, 300 steps straightforward, done also by means of simulation. You can easily add noise here also to this system, which is nice because if you remember from calculus, we were solving those equations kind of formally. Here you can solve them numerically using stochastic sampling, and you can add noise anywhere you want. You can play with noise with probability. You can view the same pictures that you saw in a Wikipedia article. I want to show the number of rabbits and foxes in the system. Here we are, over 300 steps, how they develop. As you know, the more rabbits, the more foxes, because they have food. Once they start eating the rabbits, the population of rabbits goes down, and then the foxes start to die out also. And that repeats, confirmed by measurements in the world, in the wild ecosystems. You can also derive the space diagrams, very similar, identical to what you saw in the formal solution. Stochastic sampling is very powerful, statistics in action. You can approach any precision with sufficiently many samples. Let me show you the Lorentz equation, the beautiful butterflies there. 1,000 steps. Let's look at the beautiful space diagrams. We can derive them too. Depending on which variable you are showing, you get different butterflies also. So that opens up a lot, that doesn't it? And so now I have kind of showed you indirectly what fusion in Bayes fusion is. That's been the idea from the very, very beginning of what we've been doing earlier also at the university. And the next step is, of course, continuous influence diagrams, continuous decisions for which you can optimize, find the optimal value of a continuous variable, equations and decisions in influence diagrams. Then, of course, a lot of work in learning arbitrary distributions, continuous learning equations. There's a lot of work that can be done. I've been talking for half an hour, so perhaps we can stop now and spend the rest of the time on questions and talking.
Great, Marek. Thank you a lot for the presentation and the demonstration. That's really interesting. It really opens up quite a lot of things for potential modeling. Do we have questions from the audience? You can either type in the chat or just unmute yourself and ask. While we are waiting. Oh, yeah. Hi, Helen.
Sorry if I just threw into a good idea. I just wanted to ask, so this looks amazing, and it's so, because one of the big pitfalls of BNs is we always say that they don't work well with dynamic models, and we often recommend a systems dynamic approach or something like that. So do you think that this new development is going to sort of fill that gap, Marek, in terms of making BNs more appropriate for these, or more versatile for these sort of dynamic problems?
I think so. It's just like systems of differential equations are extending systems of equations to dynamic domains. So we can do the same with Bayesian networks. We can do it now already. There's no need to wait. Actually, you can do it. Whether you have discrete models that are a favorite model that I love showing is it was a model developed by one of my doctoral students here in Białystok. It's modeling the monthly cycle, and it's completely discrete. We don't have equations for that. One thing we know is that it's a system with memory, because on day one you know roughly when ovulation will happen. So let me show you that. When you enter evidence of bleeding on day 0, look what happens. You already have the probabilities. Let me show you that. Let me select the phase. It's almost like a textbook example. When you look at textbooks and the hormone levels, you see that this picture looks almost like that. So we can model dynamic systems with memory. How do we do that? We have higher order differentials, essentially. These influences are influences of higher order. So it's equivalent to ninth order differential. It's an amazing thing. So you don't need to make it very simple, like having the Markov assumption, just first order differentials. You can have, sky is the limit, really.
Thank you.
I haven't invented all of this. It's just trying to do that, interpret it within Bayesian networks, what has been done for centuries, really.
Annemarie, there's a question in the chat as well.
Yeah, I was just about to read it out. So Pascal is asking whether there's any integration with AI. Is GPT aware of Genie and vice versa?
Yes, we've been toying with that. So the question is, what can we use the large language models for? We've tried to construct simple Bayesian networks, asking, can you build a model in Genie? And actually, we are getting models in Genie, but there are some syntactical problems. So one thing we want to do, we've been talking about this internally. We haven't done yet, no product yet, but for people who are just starting out, being able to say, I want to have a simple model in this and this domain for diagnosing my car. And the question is, will a large language models like ChatGPT create an initial Bayesian network for us? So that's one thing that we've been thinking of. Do you have any other ideas?
Well, I must admit, I actually tried that when I wanted to format my volcano data that I emailed you about recently, Marek. I was like, I asked ChatGPT, do you know Genie? How does my data need to look like? And can you write me some code to format it? So I got some answer, but I don't think it was quite right. The answer that I got, because anyway, but it did something. So it seems to be aware of it. ChatGPT does.
It's a matter of training the large language model with correct syntax and manuals, and so
So Pascal added that he asked because of Bayesian Lab actively integrating with AI and Agena as well.
We haven't looked at it, so I don't know exactly what
they're doing. Do we have more questions?
I think Gang has a question.
Sorry, Stephen, did you have a question, or is a hand up that I'm not seeing?
No, I think Gang G. Is your microphone working, Gang?
Testing.
It's a little quiet.
Testing. Very quiet, yes. Sorry. Testing.
Yeah, it's very faint.
Yes,
Yeah,
Can you type your question? Oops. In the meantime, I might just ask about, so this example here, I was just wondering how you get the phase diagram. How is that set up?
You mean the example now, the monthly
It
cycle?
doesn't matter. The one before or this one, you kind of showed.
Like here, how do we get the phase diagram? It's essentially derived also from the results, from the samples that we get. It's essentially drawing the number of rabbits as a function of the number of foxes. So, and we have both because they've been calculated over time. So we look at if you have this, for example, you have pairs of the number of rabbits and number of foxes. You have as many pairs as there are steps, 300 of them. So it's just a matter of plotting them
Right.
this way. It's easy to derive numerically. I still want to get mathematicians interested in that, people who work with difference equations, differential equations.
Thank you. We've got the question now in the chat, about the parameter estimation of a dynamic Bayesian network. How are the CPTs populated from external data sets instead of manually populating the CPTs?
Great, thank you for this question. The model for the menstrual cycle was actually learned from data. So my student Anya was very lucky because there was a big study done in Europe, I think, Italy, Germany, France, and there was several thousand of women who participated. They observed their cycle over many months. So this model is learned for a woman who had actually a cycle of 31 days. And all of the parameters are learned from data. Here is the prior for different time steps. This is all learned from data. So there is actually a way of opening a data set and populating the tables from the data set, given that you have a structure of the dynamic model. We don't have learning yet.
What might be useful is you can also use that to simulate some data, can't you?
Yes, in fact, let me show
and then
that.
What I'm after is kind of to see the structure, how the data looks for the learning, because that's the same as the data comes out in the simulation, isn't it?
Yes, you can generate data from an existing model, and you can also use that data to learn the parameters. The format is quite simple. Let me show you that in the manual. Here is an important section, tutorial more like I think it's in learning. No, it's I think here, learning the parameters. So this is the format that is used for a very simple model. You have these are records, of course, and then the variables at different time steps are essentially denoted by underscore and number. So the first variable goes here, the second here, etc. So this is the format. You need to have time series, and these are every row in this table is a time series, essentially.
Thank you. I also, yeah, you go.
Well, you can derive tables if you have equations. If you have equations, you can easily derive tables for discrete Bayesian networks. Suppose I wanted to have a conditional probability table right here. I go to the discretization tab. I specify the discretization. The parents are also specified, and you can essentially sorry, I wanted to press this one. It's essentially by means of sampling, deriving a CPT. As you see, it's each time a little bit different because it's sampling.
Yeah.
So you can, if you have an equation, you understand how the system works, you can easily, automatically derive a conditional probability table. That is definitely very handy if you have at least partial understanding of the physics or engineering of the system. No need to do it manually. You can just use the equations to do it. No
I've got a question. I mean, it looks like a really amazing playground and lots of different, options of phrasing your model or modeling different things. And you said you've had it running for about a year. Have you seen some interesting applications here that other people, chose that for their modeling? Anything published yet?
Absolutely. In fact, we are going to let me see if I have it here. Okay, here it is. I have definitely interesting models. They are going to get into our repository soon. Let me. Here is a model. This is pipeline corrosions. It's one of our users, one of the commercial users, clients. It's a hybrid model with a dynamic component. As I said, it's going to be in our repository very soon. It's a matter of days. So there are models like this that are using the hybrid modeling capacity and also the temporal capacity. So
cool. Great, thank you. There's one more comment from Pascal saying that the webinars are very useful, but he would love to see a 3 to 4 day long seminar or a series of tutorial. Is that something you've been offering on this? I mean, I know we've had one at GNS, which was really helpful. We got a group of people together, but do you still offer that quite regularly?
We teach courses, and that's one way. Although I wonder how long I could talk about just the hybrid modeling capacity. I think it's just you know everything really already because you've been learning about this in elementary, high school, and college. It's just a matter of seeing the connection, and that can be done in an hour. In fact, this seminar was probably enough to get you going with this.
I think so, yeah. Quite some. We have one more question. Does Genie make a distinction between static discretization and dynamic discretization?
No, well, so far we have only static. So for every node, like let me see if this one is discretized. Yeah, you statically define the discretization. We don't have the dynamic, and we don't have something that we want to have in the longer run. Kind of deriving the optimal discretization, optimal from the point of view of where you are interested, what you are interested in, which region of the variable. Because discretization, in theory, if you discretize it fine enough, you can approach the continuous values. But the question is how and where to discretize, and it belongs to that, future work. We know where we are going, but there's always a limited work power, and so it's not going to happen this year. Maybe next one.
We'll see. I just put a call out to any last question, and I see someone typing. Unless, John, you want to speak up? No, but thank you very much, Marek, for an interesting discussion. So maybe a good time to wrap it up. Thanks so much to everyone for joining us. Thanks so much, Marek, for your presentation and the discussion afterwards. And